Yes, students, welcome back to my video lecture 3 on P block elements. Okay, so in the last video, we discussed in detail about the variation of atomic radius, the variation of ionization enthalpy, the stability of oxidation states, and we were talking about melting point and boiling point, isn't it? We were talking about what? Melting point and boiling point. Say yes or no? Yes. So, I told you a very interesting fact about the electronic configuration. Okay, again please just have a quick glance and then we will go with the next concepts. Okay, so from gallium, indium and thallium, there are inner completely filled d orbitals and inner completely filled f orbitals. D orbitals and f orbitals will exhibit pore shielding effect. So that is why, okay, so because of the pore shielding effect of d orbital and f orbitals, the outer electrons of gallium, indium and thallium, the outer electrons of gallium, indium and thallium will be, okay, more towards the nucleus. Since they are more towards the nucleus, they will have less size, less atomic radius than expected. Correct? Okay, any doubts? Yes. So please go back and watch my video lecture 2. Understood? Okay, yes. Now, okay, what about the stability of oxidation state? From boron to indium, these elements are quite stable in +3 oxidation state, whereas thallium is stable only in which oxidation state? +1 oxidation state. I gave you the clear-cut reason. Why is that? Okay, why thallium is stable only in +1 oxidation state? Because, okay, because of inner completely filled d orbitals and f orbitals, okay, the outer electron, okay, these s electrons, the s electrons are tightly held to the nucleus. Okay, they cannot be removed easily. Hence, which electron can be removed? Only outermost p electron can be removed. Hence, thallium is stable only in +1 oxidation state. It doesn't want to be in +3 oxidation state because it is quite difficult for thallium to lose all the 3 electrons. Since the s electrons are tightly held to the nucleus, it is quite difficult to lose these s electrons. So that is why thallium will be more stable only in +1 oxidation state. Any doubts? Okay. Now I was talking about melting point and boiling point, isn't it? Didn't I? Yes. Okay. So our idea is metals always have more melting and boiling point than non-metals. Okay, so here we know boron is a non-metal, aluminium, gallium, indium and thallium are metals. So that means aluminium, gallium, indium and thallium should have more melting point and boiling point than boron, isn't it? But unfortunately, there is a reverse in the order. What is it? Boron has high melting point than other elements, even though it's a non-metal. Now my question arises here. Why boron has high melting point even though it's a non-metal? It is because of the structure of boron. It is because of the structure of boron. Look here, boron, very important. See, boron as icosahedral structure, okay, it will have 12 corners. The icosahedral structure means it has 12 corners and 20 faces. Okay, so it is because of this icosahedral structure, it is because of the icosahedral compact structure of boron has high melting point than the other elements. Okay, so which among these elements has highest melting point? It is boron. Why boron has highest melting point? It is because of its structure. What is the structure of boron? Boron exists in icosahedral structure. Icosahedral structure will have 12 corners and 20 faces. Please, okay, visualize the icosahedral structure because I cannot draw the 3-dimensional structure here. Okay, simple, understood? That's about melting point and boiling point. Now about the density of these boron family elements. Okay, what about the density of these boron family elements? Okay, yes guys, luckily there is no exception, there is no change in the density of these boron family elements. Okay, see, that means density will follow a regular trend. Density, that means boron family elements follow regular trend in density. Regular trend, there is no exception. Very lucky. Otherwise, in all other cases, if you take atomic radius, there are exceptions. If you take ionization enthalpy, there is exception. If you take oxidation state, there is exception. There is exception even in melting point and boiling point. But luckily, as I said, okay, there is no exception in density. It follows a regular trend. Okay, we know, okay, density should increase down the group, isn't it? Okay, down the group, mass increases. Okay, since the mass increases, the density should increase, because density is equal to what? Mass by volume, isn't it? Okay, density is equal to mass by volume. Okay, down the group, since the atomic mass increases, density will increase. So from boron to thallium, there is a regular increase in density. There is a regular increase in what? Density. So density increases from boron to aluminium, aluminium to gallium, gallium to indium, indium to thallium. So very, very lucky enough to say that there is no exception in the case of density order. Density order. Understood? Okay? Yes. Okay. So that's so, okay, that's so nice. Now understand one more thing. Understand one more thing, that gallium, okay, yes, gallium has a melting point of 303 Kelvin. It has a melting point of how much? 303 Kelvin. Melting point of gallium is just 303 Kelvin. So, okay, yes, look here. It melts even at our body temperature. Even at our what? Body temperature. Okay, so if you take gallium in your palm, if you take gallium in your palm, it melts, because our body temperature is more than the melting point of what? Gallium. Okay, so even if you take gallium in your palm, it's going to melt. You don't have to heat it, it will melt, because our body temperature itself is more than the melting point of what? Gallium. Gallium. Understood? Okay, so gallium, one more point, please remember, what is it? Okay, gallium is a solid. It exists as solid in winter and liquid in summer. It exists as solid in winter and liquid in summer. Liquid in summer. Okay, so guys, that is all about the physical properties of boron family elements. We did a great job. Okay, what are the different physical properties that we came across? We studied its electronic configuration, atomic radius, ionization enthalpy, stability of oxidation state, melting point, boiling point, density, and so many things. Is that correct? Okay, now our main topic of discussion is all about, okay, the chemical properties of these boron family elements. Okay, so now let us more emphasize on the chemical properties of boron family elements. We will understand the chemical reactivities of each and every element of boron family, that is boron, aluminium, gallium, indium and thallium. Okay, so now, yes, chemical properties of boron family elements. Chemical properties of boron family. Yes, okay. Chemical property of boron family. So whenever I say chemical property, obviously we'll come across n number of chemical reactions here. Okay, yes, you don't have to by heart it. It's very easy to remember, okay, all the chemical reactions. Don't by heart. Okay, so what are the chemical reactions that we come across here? Look here, reactions of boron family elements with, see this, with, okay, first one, air. Okay, whenever I say air consists of so many gases, isn't it? there is oxygen gas, nitrogen gas, hydrogen gas, etc., etc. So whenever I'm talking about the chemical reactions of boron family with air, that means I'll be talking about the reactions of boron family with oxygen and nitrogen. With oxygen and with what? Nitrogen. Then the reactions of these boron family elements with oxygen over nitrogen over with water, then with acids and bases, with acids and bases, and very, very, very importantly with halogens. With what? Halogens. So reactions of boron family elements with air, that means we need to write separately for the reaction with oxygen and nitrogen, then reactions of boron family elements with water, then with acids and bases, and then with what? Halogens. So shall we study each and every reaction? Shall we emphasize more and more about these chemical reactions? Again, I will tell you, you don't have to by heart, and more importantly, you don't worry about balancing these reactions, because we have already learnt about balancing the reactions in redox reactions. So now, first one, reaction with oxygen. Reaction with oxygen. Look at here. First reaction with oxygen. How does boron family elements react with oxygen? So we have boron, aluminium, gallium, indium and thallium, isn't it? We have already studied about the stability of oxidation state. We know that boron exists in +3 oxidation state, aluminium exists in +3 oxidation state, gallium in +3, indium in +3, whereas thallium in +1 because of inert pair effect, isn't it? Now, what happens when boron reacts? What happens when these elements react with oxygen? When these elements react with oxygen, they form oxides. They form what? Oxides. What do they form? They form oxides. Then what is the formula of these oxides? What is the formula of oxides formed by boron? What is the formula of oxide of aluminium? What is the formula of oxide of gallium, indium and thallium? So shall we write the formula of oxides? Look at here. Look, boron is in +3 oxidation state. Oxide means O2 minus. What you are supposed to do? You are supposed to cross multiply. That's it. Criss-cross method, isn't it? Therefore, the formula of this oxide is going to be what? B2O3, isn't it? Criss-cross method. Criss-cross method. B2O3. Again, aluminium is in +3 oxidation state. Oxide means O2 minus. Again, cross multiply. What is that you're going to get? Al2O3. Isn't it? Same. Gallium again in +3, oxygen in -2, criss-cross method. We will get what? Ga2O3 and In2O3 for indium oxide. Correct? But how about for thallium? Thallium, look at here. Thallium exists in only +1 oxidation state. Oxide O2 minus. Now cross multiply. What is the formula of thallium oxide? The formula of thallium oxide is going to be TLO, TL2O. TL2O, it is not, no, it is not, no, B2O3 or Al2O3 or J2O3 or In2O3. It is not E2O3. It is not E2O3. The oxide of thallium is going to be what? E2O. E2O. Are we clear? Yes. Boron will form an oxide of the type B2O3. Aluminium will form an oxide of the type Al2O3. Gallium will form an oxide of the type Ja2O3. Thallium will form an oxide of the type TL2O. TL2O. Understood? Understood? Yes. Let us write it here. So, observe this. Boron will form an oxide. When boron reacts with oxygen, it forms an oxide of the type B2O3. Correct? When aluminium reacts with oxygen, it forms Aluminium oxide of the type Al2O3. Okay, when gallium reacts with oxygen, it forms gallium oxide of the type Ga2O3. Indium, when it reacts with oxygen, it forms indium oxide of the type In2O3. Whereas thallium reacts with oxygen to form thallium oxide of the type Tl2O. Tl2O. Got it? Simple? Okay? Yes. So I can say, when boron family elements reacts with oxygen, they form two types of oxides. Which are those two types of oxides? One type of oxides of the type E2O3 and the other type of the oxide of the type what? E2O, isn't it? Gallium to indium will form oxide of the type E2O3, whereas thallium will form an oxide of the type E2O. E2O. Got it? See here, okay, boron oxide. This oxide is acidic in nature. Please remember, okay, boron oxide, okay, this is called as boric oxide. It is called as what? It is acidic in nature, whereas aluminium oxide is amphoteric in nature. It is amphoteric in nature. And the rest three, that is gallium oxide, indium oxide and thallium oxide, these three are, okay, basic in nature. Basic in nature. Okay. Boric oxide is acidic in nature, aluminium oxide is amphoteric in nature, gallium oxide, indium oxide and thallium oxide are basic in nature. Basic in nature. Understood? Understood? Okay. See, and look at the properties of the oxides of these elements. See, only impure barium. Okay, sorry, only impure boron. Only impure boron will form oxide. Will form oxide. Only impure boron will form oxide. Pure boron will not form oxide. Will not form oxide. Okay, very, very important point to be noted. Very, very important point to be noted. Okay, what is it? See, only impure boron will form oxide, not the pure boron. Okay, pure boron will not form any oxides. Okay, only impure boron will form what? Oxide. And how about aluminium oxide? See, once aluminium metal, when aluminium metal reacts with oxygen, okay, yes, it forms a layer of aluminium oxide. Okay, it forms a layer of aluminium oxide. Okay, yes, it will form a layer of what? Aluminium oxide. This layer of aluminium oxide prevents further oxidation of aluminium. Okay, this layer of aluminium oxide, okay, this is what we call passive nature. Passive nature. Okay, once, okay, a layer of aluminium oxide is formed, this layer of aluminium oxide will prevent further oxidation of aluminium. Further oxidation of aluminium. That means once aluminium oxide is formed on the layer of aluminium metal becomes passive. It becomes what? Passive. Okay, it will not further react. It will not further react. Okay, are you getting my point? That means, because why it is not, the aluminium does not further react, because, okay, see this, this layer of oxide, this layer of aluminium oxide will not allow the air, okay, this layer of aluminium oxide will not allow the air to penetrate into aluminium. Okay, it will not allow the air to penetrate towards what? Aluminium. When air cannot reach aluminium, aluminium will not get oxygen. When aluminium doesn't get oxygen, it will not get oxidized to aluminium oxide, isn't it? That means once the layer of aluminium oxide is formed around aluminium metal, aluminium becomes passive. Okay, it will stop its reactions. It will stop its what? Reactions, because it cannot get into contact with what? It cannot get into contact with air. Since air cannot penetrate into aluminium, okay, aluminium cannot react with oxygen further. Hence, aluminium becomes passive in nature once the layer of aluminium oxide is formed around aluminium metal. Aluminium metal. Okay, are we clear? Okay, so once more I will summarize. Okay, so now, all these boron family elements reacts with oxygen, okay, to form two types of oxides. One is E2O3 and the other one is E2O. From boron to indium, they form oxides of the type E2O3, that is B2O3, Al2O3, Ga2O3, In2O3, whereas thallium will form an oxide of the type E2O. Okay, boric oxide is acidic in nature, aluminum oxide is amphoteric in nature, gallium oxide, indium oxide and thallium oxide is basic in nature. Basic in nature. Understood? Okay, only impure boron will react with oxygen, not pure boron. And once aluminum forms a layer of aluminum oxide, okay, aluminum will become passive. It will not further react, because aluminum oxide will become a coat. It will act as a coating around aluminum and prevent further oxidation of what? Aluminum. Okay, so that is what we call the passive nature of aluminum. Okay, any doubts? That's nice. Okay, now let us go and learn the next chemical reaction of these boron family elements. What is the next reaction? Reaction with nitrogen. Reaction of boron family elements with nitrogen. Okay, reaction of boron family elements with nitrogen. Okay, yes, again very simple reaction. Look here. So we have boron, okay, aluminium, gallium, indium and thallium, isn't it? Again, boron is in +3 oxidation state, aluminium +3, gallium +3, indium +3 and thallium +1, isn't it? Correct? Okay, yes. See this, gallium, indium and thallium, these three will not react with nitrogen. Will not react with nitrogen. They will not react with nitrogen. Are you getting my point? Okay, gallium, indium and thallium will not react with nitrogen. Only boron and aluminium reacts with nitrogen. Okay, got it? Only boron and aluminium reacts with what? Nitrogen. Yes, yes. Look here, boron and aluminium reacts with nitrogen to form what? To form nitrides. Okay, nitrides. Now, what is the formula of nitride then? See, I told you, boron is in what? +3 oxidation state. Nitrogen will be in -3 oxidation state. So what are you supposed to do now? You are supposed to cross multiply. Yes, correct. So it becomes B3N3, isn't it? Okay, 3 is common factor. So that means the formula of boron nitride is going to be what? Bn, isn't it? And also aluminium. Aluminium also exists in +3 oxidation state. Nitrogen will be in -3 oxidation state. Now cross multiply. Okay, what is that you're going to get? Al3N3. So here 3 is the common factors. Therefore I can say, okay, aluminium will form nitride of the type Aln. Understood? Okay, so only boron and aluminium reacts with nitrogen to form nitride. Okay, what is the formula for boron nitride? Bn. What is the formula for aluminium nitride? Aln. Boron nitride Bn and aluminium nitride Aln. Are we clear? Okay, yes. Now see this, if boron nitrides combine themselves, boron nitrides come together, if all the boron nitride molecules, like this, if boron nitride molecules come together, okay, they form a long chain. They're going to form a long chain. Okay, yes, it is of the type BnX. And if X is greater than 3, if X is greater than or equal to 3, then the association of all these boron nitride molecules, it is called as inorganic graphite. It is called as what? Inorganic graphite. Inorganic graphite. Are you getting my point? Okay, yes, understood. So if the boron nitride molecules come together, they're going to form a long chain. They will form a long network like structure, okay, which will be similar to what? Graphite. Then that is called as what? Inorganic graphite. Okay, what is the formula for inorganic graphite? It is BnX, where X is greater than or equal to what? 3. X is greater than or equal to 3. Understood? Okay, if all the boron nitride molecules come together, if they come together, they form inorganic graphite. Now, what happens when boron nitride and aluminum nitride are hydrolyzed? Okay, what happens when boron nitride and aluminum nitrides are hydrolyzed? We know when any nitride is hydrolyzed, hydrolysis means reaction with water, isn't it? When any nitride is hydrolyzed, ammonia gas is liberated, correct? When any carbide is hydrolyzed, okay, methane gas is liberated, isn't it? CH4. When any phosphide gas is hydrolyzed, it will form what? Phosphine. Correct? Okay, yes or no? Correct. When any hydride gas is, when any hydrides are hydrolyzed, it will liberate what? Hydrogen gas. So like this, when any nitrides are hydrolyzed, ammonia gas will be liberated. When any carbides are hydrolyzed, methane gas is liberated. When any phosphide gases, okay, when any phosphides are hydrolyzed, phosphine gas is liberated. When any hydrides are hydrolyzed, hydrogen gas is liberated. So now we are talking about the hydrolysis of boron nitride and aluminum nitride. What happens when boron nitride is hydrolyzed and what happens when aluminum nitride is hydrolyzed? Okay, so in both the cases, ammonia gas will be liberated. In both the cases, ammonia gas will be liberated. Okay, boron nitride is hydrolyzed, ammonia gas is liberated. Aluminum nitride is hydrolyzed, ammonia gas is liberated. Along with this, it's going to form what? BOH thrice. Okay, and along with this, it's going to form ALOH thrice. ALOH thrice. Okay, ALOH thrice. Are we clear? Okay, boron nitride, when it is hydrolyzed, when any nitrides are hydrolyzed, ammonia gas will be liberated. Okay, note this point. So when boron nitride is hydrolyzed, ammonia gas is liberated. When aluminum nitride is hydrolyzed, ammonia gas is liberated. Okay, along with the formation of boric acid and aluminum hydroxide. Okay, understood? So that's all about the reaction of, okay, now boron family elements with nitrogen. So gallium, indium and thallium, these three will not react with nitrogen. Only boron and aluminum will react with nitrogen to form nitrides of the formula Bn and Aln. So if boron nitrides come together, they form inorganic graphite. When nitrides of boron and aluminum are hydrolyzed, they liberate nitrogen gas along with the formation of boric acid and along with the formation of aluminum hydroxide. Okay, yes. Next, students, so that's all about the reaction with nitrogen. What about the next reaction? Reaction of boron family elements with water. Okay, see, understand this. No boron family elements will react with water. That means boron does not react with water, aluminum does not react with water, gallium does not react with water, indium does not react with water, and thallium. That means no boron family elements reacts with water. There is an exception here. Except aluminium. Except what? Aluminium. No boron family elements reacts with water except aluminium. Aluminium reacts with steam. That means what? Steam. That means hot water. Okay. Even aluminium does not react with cold water. It does not react with cold water. Aluminium reacts only with what? Hot water to form what? Yes, aluminium oxide, and it liberates hydrogen gas. It liberates which gas? Hydrogen gas. Only aluminium reacts with hot water to form aluminium oxide and it liberates hydrogen gas, whereas no other elements of boron family will either react with cold water or with hot water. They do not completely react with water except aluminium, which reacts only with hot water. It does not react with cold water to form what? Aluminium oxide, and it liberates what? Hydrogen gas. So guys, so that is all about some of the chemical properties of boron family. We discussed the reaction with oxygen, we discussed the reaction with nitrogen, we discussed the reaction with water. In the next class, we discuss the reaction of boron family with acids and bases and with halides. Okay, thank you.